So the title of my talk. So I'm from north of Spain, and I was my task is becoming more easy because after the presentation of Larissa, because she already introduced you in magnetic microwires. You can see here the map of Spain. Here we are, San Sebastian, very near France. This is our most members of our group, and in fact, I want to say that here is one of the last meeting in which Professor Fert, Nobel Prize for Physics, is present because he is now a distinguished researcher and belongs to our group. You can see also outline of my talk, so I will make some short introduction, but it should be short, and then because of the previous talk. And I will speak about way to tune magnetic properties and JMI effect by stress-induced magnetic stress annealing induced magnetic annihilation. So in fact, we working with magnetic wires. Magnetic wires are known since many years, but we working with family of so-called glass-coated microwires. This is the thinnest amorphous materials which could be produced by rapid quenching technique. So previously, some crystalline materials were developed, and in our case, we have perfectly cylindrical shape and diameters, dimension of from sub-micrometric to a few micrometer size. You can see here the diameters, and it could be produced almost in continuous way. And in one of such bobine, you can have few kilometers of continuous microwires. And here you can see the view of the most recent setup which we have in our spin-off company in San Sebastian. And that materials present different features, quite attractive for applications. For example, they can present fast dimensional propagation, excellent magnetic softness, and high magnetic impedance effect. They are mostly biocompatible because of glass coating, because glass is biocompatible with human body. It could be useful for medical applications. And even recently we tried to produce crystalline materials for Hostler type alloys or with granular structure, and this could be useful for different applications. So since the alloy could have different composition, we can have different magnetostriction constant. This already was mentioned by Larissa. And for example, with composition with nearly zero magnetostriction can present this almost linear hysteresis loop with very low coercitivity, while the iron-rich materials, which in fact are much less expensive and could be much cheaper, present this quiet hysteresis loop. And this is because this picture demonstrates that if you change the relationship between iron and cobalt, you can tune the magnetostriction coefficient of our material. So these cobalt-rich materials can present quite large giant magnetic impedance ratio, giant magnetic impedance effect, which is suitable for sensor application. Iron-rich materials usually are interesting for very fast dimensional switching with velocity up to 2.5 kilometers per second. But I already mentioned that cobalt is much cheaper, and iron-rich is much cheaper, and cobalt belong to critical materials. Therefore, there are some demands to looking for some post-processing to improve the magnetic softness of iron-rich materials. This is the main motivation of this work. So the question is that if we can find the way how to change this hysteresis loop to that one and improve the giant impedance effect from this very poor performance typical for iron-rich materials, because the permeability in this region, low field region, is quite low to that one. And we tried, and recently we published a few successful attempts, and this is the content of my talk. So in fact, iron-rich materials present this kind of domain structure with a single domain responsible for this fast domain wall propagation. So once we change the external magnetic field from let's say positive to negative, at some point we have create the domain wall which propagates very fast the materials, and then we can have that perfectly squared history slope. This is real loop, so as you can see, it's almost perfectly squared. And this is shape is responsible for the very fast domain wall propagation. So for in tune the magnetic properties, there are different possibilities. One is kind of irreversible. You can choose the composition, geometry of materials, and then you can choose another one to fit the requirement of different applications like heating, thermal treatment, etc. So this is the content of. Larissa already mentioned about magnetic impedance effect. So it could be quite high in this kind of materials, up to, in this case, about 500%, but it could be even higher. And the origin of this effect consists of the skin effect of magnetic conduct. And generally speaking, the penetration depth of skin depth depends on magnetic permeability. Therefore, soft magnetic materials is essentially important for this kind of applications. And the general picture, this is the cross section of microwires. We increase the frequency. The current is now flow near the surface, and then if you now apply magnetic field, you can change the sample impedance because the area which flow in the current change under the effect of external magnetic field. And it's important that this effect is essentially related to the of materials. So the GMI performance is affected very much by hysteresis loop of that materials. So if you're able to achieve very soft magnetic materials with high permeability, we can probably enhance the giant magnetic impedance effect, and this is what we rated in this group. You mentioned that this is essentially surface effect. This is calculated dependence of skin penetration depth from magnetic field. So you can see the change for quite a large, from about 1 micrometer. This is 22 micrometer diameter microwire to less than 1 micrometer, and then grow up to a few micrometers. So it's field dependent. And if you now plot minimum skin depth versus frequency, you can see that it's decreased with the frequency. So I already mentioned that we tried to improve the properties. This is, in fact, of course, the most important that you can try to relax the internal stresses. And in the case if you just anneal your samples in the furnace, you can have just small variation of properties, but the hysteresis loop shape remains the same. So hysteresis. So it's still rectangular, but some decrease of coercitivity is observed because you somehow relax the stresses. However, they recently found that if you apply stress during the annealing, you can find that the hysteresis loop become different, so coercitivity drastically drops and the permeability increase. So here is also the plot. This is one of the first paper. And then once we measure the magnetic impedance effect, this is dependence of magnetic impedance ratio on magnetic field, we observe this huge growth of the magnetic impedance effect. So recently we studied this effect of such treatment in more details. And what we found that there are different features. For example, this is the same stress applied during annealing, and we change the temperature, and we can vary the hysteresis loop from this one to almost linear. So there is a lot of possibility to tune the hysteresis loop of that material. And of course, the GMI effect we've improved still further, because you can see the difference is almost 1 order of difference in maximum value of maximum magnetic impedance ratio from this one to this one. And changing the composition, the conditions of thermal treatment, we can also tune the magnetic field dependence. This is fixed frequency, 500 megahertz, and you can see the curves are different for different kind of annealing. This is the same, in fact, hysteresis loop. So the largest field of maximum corresponds to the largest magnetic anisotropy field. And of course, not only GMI ratio, but also of the diagonal component could be drastically improved. So this is of the diagonal component of magnetic impedance effect after different thermal treatment. And it's also depend not only on temperature, but also on stress applied during the annealing. Here are two different curves. This is smaller stress and this is higher. So it has increased stress during the annealing is increased magnetic anisotropy. And also we tried to see what happened if we applied after annealing, after stress annealing, further annealing. So it's this stress-induced anisotropy is only partially reversible. So part of this stress annealing-induced anisotropy still maintains in the material, still keep in the materials. And of course, it's quite interesting because you can, in this way, to tune properties, and it could be even temperature stable. To resume, this stress annealing-induced anisotropy depends on temperature, on stress during the annealing, only partially reversible. And of course, it's a promising method for my optimization in iron-rich microwires. Another advantage of that materials is if we compare cobalt-rich materials, this is frequency dependence of giant magnetic impedance ratio. For cobalt-rich materials at low frequency is still better. That for higher frequency region, these iron-rich stress annealed samples become better than cobalt-rich materials. In this case, we plotted maximum giant magnetic impedance ratio for different frequencies, and we can observe dependence. How much time I have? Because I have 5 minutes. Okay. So another important issue, so for sensors, for magnetoelastic sensors, it's important to stress dependence of magnetic properties. Here is the as prepared iron-rich samples which we employed for these studies, and we applied the stress during the measurements. So this is without stress, and on the application of stresses, increase of crossivity and was observed, but the shape of hysteresis loop was different. What happened now if we apply stress to stress annealed samples? So under stress annealing, our samples is no more magnetically bistable, like shown in these pictures. It's close to bistable, but not bistable. And now, if you apply the hysteresis loop, became again bistable, even on the small applied stresses. So this is with the lowest volume, and then for increased stresses, it's behave like similar to as prepared sample. So in this case, applied stress is quite relevant because it allows to improve the stress sensitivity of that material. So if you plot dependence of crossivity on applied stress, this is as prepared materials and the stress annealing. So you can see the variation is much stronger in the case of stress annealing samples. So for application for magnetoelastic sensors, it's quite important, quite relevant as well to have this stress annealing induced magnetic anisotropy. Oops. And for understand this way, this was my question to Larissa. We have to take in mind that materials have strong internal stresses. So once we cool together metal and glass, they have quite different thermal expansion coefficients. And this is schematic picture of the fabrication. So once both glass and metal shrinks, the metal is subjected to strong internal stresses, and this is the calculation. So the most important one are the axial one. So this is the radius of an inner of metallic nucleus. So this interface between glass and metal, and the strength of this internal stresses increase with the thickness of glass. Of course, it's obviously because if glass is thicker, the internal stresses are thicker. And now to understand this behavior, we have to, so this is spontaneous magnetic bistability and as prepared sample. So in this case, I just reproduced this schematic picture. The axial stresses are almost the highest in the whole diameter. Now, if we subject these materials to stress annealing, we somehow, because of back stresses, is one of the origin of this stress annealing induced anisotropy, we make it almost similar axial and radial stresses. And now, if we applied stresses during the experiments, during the measurements, we recover this hysteresis loop because the axial stresses become again the highest one, and this can explain change of shape of hysteresis loop and also the stress sensitivity of our materials. Another important issue, so it might be a couple of slides more. So we were able, using stress annealing, to make so-called graded magnetic anisotropy. Conventional ways for sputtering, for example, if you change the composition during the process. In this case, well, we applied a method when we varied the temperature in the area where we place our materials subjected to stress annealing. So this is the length, and the temperature was varied, so it's kind of temperature gradient. And then once we stress annealing the sample under these conditions, we have different histories, local history slope in different regions of microwires. Here, for example, the temperature, here is just length of microwires, and history slope measured at different temperatures. And so it's important, for example, one of the examples which we published recently in Acta Materiale is that, for example, this is as prepared materials. In this case, well, this is the dependence of demand wall velocity on magnetic field, so you can see that it's quite linear, quite high, and we measured it using 6 stones method. So once the demand wall passed through the pickup coil, you can see these peaks in the pickup coils reflecting that the demand wall moves along the sample, like shown in this picture. So first, second, and third coil. And now if we apply local annealing, for example, we apply stress, heat sample on one place, we can create defects, which shown here. So this is the profile of the nucleation field. So in this case, in this place, we can inject the demand wall on the application of external magnetic field, and now the software magnetization change. You can compare these peaks now. First and third, I think, first and second peak appears simultaneously, meaning that this is the same sample, and now nucleate in different place, and then you can observe propagation of several demand walls. So we have on kind of artificial, let's say, defects or more soft magnetic region in our material. So this is another possibility to use the stress induced anisotropy for the different applications. I already mentioned one of the origin is kind of back stresses. In this case, on the stress annealing, we create compensative compressive stresses, and these stresses compensate originally axial stresses inside of the materials. But there are different models this kind of stress-induced anisotropy. For example, one of these is orientation of the pairs, of magnetic pairs, pair ordering, so-called. In our case, we have only one material, therefore this origin is hardly applied. The other one is just change of topology in level of local structure, which produce this kind of stress-induced stress annealing induced anisotropy in this kind of materials. So in fact, I pay attention only some small part of properties of the materials, and tomorrow I will have plenary talk, which I will speak on different aspects of that materials. And also I wish to mention that also for example, we can have Hosler type alloys, for example, nickel, manganese, gallium, and or we have giant magnetic resistance in that kind of materials with granular structure and even condo-like minimum, but this is a different topic, even magnetically hard materials. So I wish to finish my talk with some short conclusions. If you have, if you're interested, you can look for even some books. So the most important that with stress annealing induced anisotropy, we can tune the properties, improve the giant magnetic impedance effect, and also create graded magnetic anisotropy. And so this is kind of promising technology. And last and not least, if you're interested, you can. So now we have open two special issues. One is in processes, another in sensors. So if you're interested, you can send your papers for publication. Sensors is Q1 journal. So interested, you're welcome. Thank you again.
Okay, thank you, speaker.
Thank you for this very interesting talk. You mentioned that some of these annealing and stress annealing processes are somehow possible. How do you actually realize the reverse process.
In our case, after annealing, we just at the same conditions we annealed the samples without stress, just to relax the stresses. So in fact, I showed only one picture. We published separate paper about it. So we stress annealed the samples under different stresses. And in some cases, in the case of the higher stresses, the anisotropy was stronger. And then after that, we annealed our samples with the same temperature, but without stress. We tried to recover the initial hysteresis flow, but finally it was recovered only for small volumes of stresses. So for small stress volumes during the annealing, it could be recovered, but for strong enough, it looks like there are some irreversible changes of maybe short atomic order or something like this.